Hello everyone, my name is Marcio. I'm a master's degree student at IMP in the System and Space Engineering and Management area. Today I will talk about the study a hybrid machine learning process for anomalous satellite telemetry behavior detection. My co-author is Dr. Wouter, who is my mentor as well, and then I hope that you all enjoy it. Well, the main objective of this study is to determine a machine learning process that allows us detect anomalous behavior in artificial satellite telemetry data with a certain level of certainty. Here on the right side we have a diagram which I call the objective pyramid. It shows the construction of objective by objective until we got to the top. At the top we have this support satellite operations, which let's say it's the horizon of this study. So second, getting back to the text, second here we have generate inputs for anomaly diagnosis process. So it means that I expect that this study I'm presenting to you will generate inputs for anomaly diagnosis algorithm here. And this algorithm will provide reliable information that will be used to support the operation of artificial satellites associated with the specialist knowledge. We know that artificial satellites usually provide important service like telecommunications and natural resource uh, monitoring and so on. And these kind of services are those ones that we would like to keep working properly. And in order to that, we have to monitor the satellite, and monitor translate to into telemetry data analysis, telemetry data monitoring. But the trick here is that as big as the satellite gets, bigger is the data amount. So many telemetry signals, like more than thousands, and analyze all this telemetries, it turns to be laborious. And this scenario can jeopardize the analysis of data when it comes to detection, diagnosis, and prevention of anomalies and failures. So in order to that, that's why I'm studying this. This study it was conducted under the telemetry data from CBERS 1, which is this beautiful guy here on the right. And this study scope is limited to the power supply subsystem, which means that we analyze only the telemetry signals from that subsystem, and that's due to the fact that in the literature you can find uh, authors saying that most of the times when we have a loss of mission failure, it's because of that subsystem. It's something happened with that, so it's a subsystem that we should look carefully. And as I'm going to be talking about anomaly all the time, I would like to define a ground base here. So anomaly is considered as a pattern in the data that do not conform to a well-defined notion of normal behavior. And another thing is that in the literature you can find anomaly being interchanged for outliers. So yeah, they can be used like that. The machine learning process I propose here is divided in four parts. The first one talks about data preparation. So we get the raw data, we eliminate telemetry which are not needed, for example, from another subsystems. We remove the trivial outliers, which it's like we remove the noise part, or at least part of the noise that will interfere on the modeling for the algorithm, and we do the normalization to bring everyone to the same level. And when I say everyone, like the telemetry signals. After the data preparation, we perform a dimensionality reduction, or you can call it as a feature reduction as well. So, for example, the power supply subsystem in this case had 14 dimensions or features, and I would like to reduce it to at least 3 so we could plot and look at the data like in 3 dimensions. And in order to do that, I use the KPCA, and besides the number of components, which was going to be 3, the other hyperparameters like the kernel or gamma, they were defined based on empirical process like try and test. The next, let's go. The next step, it would be clustering, performed by the DB scan. This clustering will provide us cluster labels, which will tell us like, okay, this data point, it's from this cluster, or this data point belongs to that cluster. And also this data point doesn't belong to any cluster, so that would be kind of noise. And the last step, it will be taking these labels, let's say this clustering labels, and use them for perform the classification. So the KNN will be able to tell us if the test data points are like from one cluster or from other cluster or from no cluster at all. I would like to just mention that the whole experiment was conducted in the Jupyter notebook, and also I didn't focus in developing tools, but instead I used third-party libraries because they would allow me to focus on what is exactly the goal here, which is the defining the process itself. This is the plot of the number of features versus percentage of variance explained for the KPCA. So you can see here like the number of features or dimensions and how much of the variance we can explain with that. As I said, I was intending to use 3 since from the beginning, but I was curious about like how much difference would be other components if other components would be added, and you can see here that not much. Here on the left side, we have the data set output from the KPCA process. So from here you can see like clear that we have some grouping, some clusters already being formed. So after the clustering, what we look for is that the clustering algorithm find those guys and define them as clusters, and that's what happened here. Like we have this cluster, this cluster here, this other cluster up here, and we have this cloud of points that doesn't belong to any cluster. Well, they kind of belong to one cluster as well, which is the noise cluster. And this result is good because the algorithm was able to clusterize the points that we wanted together. So we can say that those different clusters, they represent different circumstances of the satellite, like really circumstances in the physical world, not just data points. These circumstances, they are sunset, eclipse, twilight, and of course the noise. And you would say like, but Marcio, we have 4 clusters. Yeah, we have like 1 eclipse, 1 for sunset, and 2 for twilight, because there's a transition from these 2 states, like eclipse to sunset and sunset to eclipse. So 2 transition states, 2 more clusters. Here we have the results for the KNN classification. In the left side here, you can see the plot I made back there to identify which was the best value for the K hyperparameter. So it's a K versus accuracy curve, and here you can see that any K within 3 and 6 would provide us a very good accuracy. So I chosen 3. After running the classification over the test data set, we received the output, the outcome of it, and the outcome can be seen in this confusion matrix. In the principal diagonal, we have the correct values. So, for example, it classified 9 values as noise, and they were noise indeed. And here it classified 135 points as eclipse, and they were that indeed. And when you have a value outside of the principal diagonal, it means that it was an error. So you can see here that it considered 3 eclipse data points, but actually they were noise. So this is a error from the KNN classification model. So with this, we can conclude that the lack of bigger and continuous data set until a certain point harmed the classification skew of the model because I had to use just 1 month window. But well, however, the sample used were enough to verify and validate the chosen machine learned procedure over the anomalous behavior detection. And the data processing at the beginning showed to be crucial during the early stages. Yeah, the hyperparameters tuning through the empirical methods was laborious for the KPCA, for the DB scan. And well, considering the proposed framework, the anomalous behavior detection can be made, but to assess whether the anomalous behavior is a failure or a noise or even an unknown failure, a next step in the process has to be add, some kind of analysis of the failure. Well, that's the presentation. I hope everyone enjoyed and found it interesting. If anyone has further questions, please send me through the email that it's down there. And thank you for your time.